Okay, welcome everyone to the ZAG seminar. We're very pleased to have my friend and colleague, David Favero from the University of Alberta, to speak on path homotopy quiver algebras and mirror symmetry.
Yeah, thank you, Chuck, for that introduction. And thank you to Ivan and the other organizers for inviting me to speak today. Yeah, today what I want to talk about is something called, as Chuck just said, and as it says on the screen here, path homotopy quiver algebras. So that's a made up name. Jesse and I think this is the appropriate name for this thing. And it's this is joint work with Jesse Wong, and the paper doesn't exist. Okay, so hopefully we'll have something in writing soon enough. So what I want to do is I want to sell you on this idea, path homotopy quiver algebras. So the plan is a friendly intro to these things, path homotopy quiver algebras. I'll tell you what they are. And then finally, because this is an algebraic geometry seminar, I'll talk about some algebraic geometry. But really, this is mostly algebra and algebraic topology for a good portion of the talk. We'll have some applications to really these things to mirror symmetry. And I'll focus on the example of P2. It's going to be similar to an old story of Bondal and the story of Fang, Liu, Troyman, and Zaslow. And then I'll also have a non-toric example that fits into our framework. This is green plus or mirrors. I'll explain in this framework. Okay. So really, this is kind of an algebra or an algebraic topology story for the good first portion of this. So we'll start with the definition. Maybe a quiver is a directed graph. And for and we allow loops. So quiver, I'm going to denote by Q. And we allow loops. Sorry, we allow, let's say, multiple arrows in our graph. Okay, but maybe for simplicity, no loops, and everything is finite. So really, this is the end of my big parenthetical here. Okay. So the quiver looks like something like this. So I'm going to label the vertices E0, E1, 2. Maybe have some kind of X, Y, and Z called arrows. And then we have, so we'll fix a base ring. Maybe I allow any ring here, but I'll say K. You can think field if you want, or Z. And then we're going to let KQ. Sorry, I'll try to monitor the chat, but you can also chime in if I miss something here. And please feel free to ask questions. This is supposed to be kind of introductory style. So KQ is going to be just the free vector space, K to the directed paths. This is the free module, free K module with that basis. And so in the example, KQ is just K to the, I got each of these vertices, and then I have the paths X, Y, and Z, and then I have XZ and YZ. Okay. So all these concatenations too are part of this thing. And this has an algebra structure. So first I need to notation h of a. So here's my arrow x. Right, here's h of x here. And here's t of x. This vertex here. Okay, so this is head of the arrow, tail of the arrow. And we get a K-algebra structure on KQ is given by A, B is going to be, if A and B are arrows or paths, then this is the concatenation. Okay, if the head of A equals the tail of B, so this is A, B, this is A, B, and zero otherwise. Okay, so this is some non-commutative algebra, and then this is extended linearly. All right, so that's the path algebra of a quiver. Now, now imagine the quiver is embedded in some topological space. Okay, then I can form an ideal IX, really depending on this embedding, but we'll just call it IX. Is going to be P minus Q, such that P is path homotopic to Q in X. So then I can have a definition. KQ mod IX is a thing in my title, a path homotopy quiver algebra. Right? Okay, so it's just the some paths, some set of directed paths. It's kind of like a directed fundamental groupoid. Of course, it wouldn't be a groupoid because you don't have the inverse maps. It's directed. So this is this thing. So let's do an example. If I embed A, B, C, D into a disk, then then the ideal IX is going to be AB minus CD. Okay. Questions? Okay, so this is this nice simple thing. And then conversely, consider an ideal I of the form P minus Q. So some ideal generated by relations of this form, P minus Q, where, you know, of course, you have to have that the head of P equals the head of Q, and the tail of P is the tail of Q. Okay? And we got to put one more condition. If A times p minus q is in I with head of A equals tail of P, which is also the tail of Q, then P minus Q is in I. So the picture is here, we have P, Q, or maybe homotopic in the space X, and we have this arrow A. If these two paths are homotopic, then of course P and Q are already homotopic. Okay. So question. Given such I, can we find X such that, really, can we find an embedding of Q in X is such that I equals IX, right? And this is an easy question. The answer, yes. So for example, take a CW complex. Zero skeleton, vertices, one skeleton, it's arrows, and two skeleton is these glue discs for each relation. Okay. All right, well, maybe that wasn't a very exciting question, but at least it gives us this equivalent definition. If A, yeah, let's start on a new page. Definition, an equivalent one. If I is an ideal in KQ, satisfying a star and star star, whatever those were. It was just of an ideal of the form P minus Q, and A times P minus Q in I implied P minus Q is in I. Then A equals KQ mod I is called this thing, but a path homotopy quiver algebra. Okay, very good. So I want to come up with a more canonical embedding of Q into some space X. Want a more canonical X. So for this, I'm going to consider the category C. So from now on, we're only considering quiver path homotopy quiver algebras. So fix A equals KQ mod I a path homotopy quiver algebra. Okay, that's what A always means from now on. Okay, so now consider the category CA Okay. So objects are going to be vertices of Q. And morphisms, so if V and W are vertices, this is going to equal paths from V to W in A, right, up to the equivalence in A, okay? But just paths, we don't allow linear combinations, okay, in this category. This is not a category over this base ring. It's just some category. It looks kind of like a directed fundamental groupoid, this category. So then we define XA is going to be the nerve of this category. Okay, so I'll remind you what that is. So let's say, I'll write here again, XA equals nerve CA. So for a nerve, zero simplices are objects, right? Which for, so this is general category, this is for CA. These vertices. Unsimplices are morphisms. These paths. Two simplices are compositions. It's like two paths. U. You get this two simplex. Okay, and so on. Three simplices are triple compositions, and you get a tetrahedron. So I do an example. If I go back to this original example, X, Y, A, B, and I is X, Y minus AB, then XA, this nerve, I just fill it in. So that's my one skeleton, is just the quiver. Actually, not true. There's another line here in the one skeleton, and then it fills in. So this path here is XY, but it's also AB. Like there's only one, the composition of X and Y is the same as the composition of A and B. Okay, so I got this square, which recovered this algebra as its path homotopy algebra. Okay, so I want to go on to a more interesting example. Pretend this isn't an algebraic geometry audience and won't say where this example comes from. So Q will be balancing quiver for P2. Oh, I said I wouldn't say where it came from. This is just some picture. Okay. And I is going to be the ideal XY minus YX, Z minus ZX, where these things make sense, right? So XY, YX, XZ, CX, and YZ, CY. So I added the commutativity relations. Okay. All right. So now let's draw this picture XA. And that well. I wanted it to look more like a square. Okay. Okay. So this here is the path XY, which is also YX. This is, oh, did I get it wrong? Shoot. I got it wrong. Divide them this way. So this line doesn't. Sorry about that. So actually, this is XZ or ZX, right? This here is, well, YX or XY. And here, this is YZ. Okay. So what I'm trying to tell you is that this thing is a torus. This is equal to S1 plus S1. And really it's just this torus. But I've subdivided some of these squares. Right. Okay. Maybe one more example. So it's going to just to demonstrate that this thing is a little funny. This is XYZ, and I is, even if I is 0, I get this kind of picture like this. X, Y, Z, and then XT. Okay. Okay, so I want to talk about two results with Jesse on path Homological river algebras. So one is you get I'll put cellular, but I want to explain what that means. Projective resolution of A as an A tensor A module. And two, we get a comparison between the A modules and sheaves on XA. Okay, so I'll be more specific. So I'll start with the result on the resolutions. So I need a definition. So I'm going to define this thing. A simplicial complex is pure of dimension D if all maximal cells C1, C are D cells. And as such, a complex is shellable. I forgot to write this in red here. If there exists an ordering, I'll pretend they were already ordered, such that if I take the previous cells and intersect it with the new cell, this is D-1 dimensional. Okay. All right, whatever. So that's some definition. So it's just a kind of a standard condition for simplicial complexes. So we can forget it. It's very close to what's called a Cohen-Macaulay simplicial complex. So here's our theorem. There exists a natural cellular resolution, and I'll somewhat explain what that means. Resolution P of A as an A tensor A op module. So as an A bimodule, such that the rank of PI is equal to the number of I cells in XA. Okay, but now what does this shellability condition give us? So if we want this to be a general theorem, but we need this condition right now. So if XA, like I said, this is in progress. If XA is shellable, then one, A is causal, and two, let me move this up a little bit. There exists a sequence of simplicial collapses XA to XA bar, okay, such that the corresponding Morse complex is the minimal resolution. So I'll just say that this means, in particular, we find this XA bar such that the rank of the ith term in the minimal resolution of A as an AA bimodule is equal to the number of I cells of XA. So this is not even a regular CW complex, but it is a CW complex with some decent properties. Okay, so we find this space. And it exactly reflects this. Okay, well, okay. So I want to also talk about sheaves on XA and XA bar and compare those to A modules, okay? So this space is somehow nicely related to the algebra of this, just the pure algebraic facts about A. Okay, so I'm going to move on to next. Comparing A modules and sheaves on XA slash sheaves on XA bar. Okay. So for this, first I need to define something again. So for each vertex, let CV be the category of paths in Q, so not in A, okay? Starting at V, okay? So maybe it's bad notation, but anyway, it's at least short notation. But CA, remember, was paths in A. I want this CV for a vertex to be paths in Q. So like, for example, if I have this quiver like this, like Q, X, do my vertex V here, and then I look at Y and Z, maybe W here, okay? So this CV is not just this, it's paths in Q. So CV looks like this picture here. So it's really trees coming out of V in this case, okay? All right, so I'm going to define this a map pi V. Goes from the nerve of CV to the nerve of CKQ to the nerve of CA. Okay, it's the composition. Okay, I'm going to define TV to be the push forward of the constant sheaf K. How is CV a category? So objects, it's just like CA. Thank you. So objects are these points. These are objects. And these are morphisms. Okay, and there's also this composition and this composition are morphisms. Does that make sense? So there's only finitely many objects and morphisms in this category. Thank you. Okay. So I have this map pi v, and I'm defining, was that okay? Did that answer your question?
Yeah, that will do.
Okay, thank you. Okay, so I'm going to just define this. This is a sheaf. This is, remember this was called XA. This is a sheaf on XA. Okay, it's in fact, this is a, let me insert a word here. I think I can cheat and do that. Not quite. This is a constructible. Sheaf. So this is just a constant sheaf. If I take it push forward, I get a constructible sheaf on XA. Okay. Constant sheaf. Okay. So the theorem is there is an equivalence categories, derived category of A, equivalent to TEV, which that V is in B. And this is a whole subcategory of the derived category of sheaves on XA. Okay. And also, I'll put shellable case. So you can look at their image under a simplicial collapse of all these objects. You can push them forward further under the simplicial collapse in the shellable case. Shellable case. Okay. So this thing is the derived category of A. I don't really have time to talk about that. You can think about this as roughly the category of A modules, okay? Objects are complexes of A modules up to quasi-isomorphism. This is roughly the category of sheaves, but we have to do this deriving thing. Okay. For this statement to be true. So I've embedded the category, essentially the category of modules on A into sheaves on XA. Why is this interesting? Well, first, let's, I said, finally, I'll get to algebraic geometry. And I guess I didn't lie because I think I'm there. So let's talk about application to algebraic geometry. Okay, so I'm gonna let L1 through LT be line bundles on a torque variety X sigma. Okay, so that means therefore Li is full of Di, where a Di is in the class group X. Okay, and then recall the Cox ring of X sigma is K adjoin X1 to Xn of the n is the number of rays you can, is a CL is graded by the class group. This is a graded ring, okay? So, and in fact, Ham from Li to Lj in sheaves on X sigma, right, is just a graded component of this Cox ring. I should probably assume I have no torus factors for this to be true. So let's assume that. Okay. Take a drink. I'm losing my voice. So we can make a quiver. The vertices are L1 through LT. And the arrows are given by, if I have a monomial, so I have a monomial in here, is going to give me a map from Li to Lj. Call this arrows are going to be denoted by A, and I'll call this monomial M of A. Okay, so arrows, the monomial is the corresponding monomial in here is M of A for an arrow. So I get a map M from paths to this polynomial ring, really to monomials in this polynomial ring. It sends composition of paths. So sorry, this should be, the arrows should be right, indecomposable map. So you can't write it as a composition, okay? So then I can extend this map M to all compositions, paths, by just producting my monomials. Okay. In fact, this is a map of posets from the path poset to the monomial poset. And I define an ideal I be P minus Q such that M of P equals M of Q. All right. Hey, so from this, I got, guess what? Then the endomorphism algebra of the sum of those line bundles is KQ mod I. And 2, KQ mod I is a half homotopy quiver algebra. Okay, so these things appear in algebraic geometry, at least as endomorphism algebras of sums of line bundles. Okay. So maybe shellable examples. No justification. I equals 0. So i.e. A is KQ. So any quiver, if you don't put relations. If you take O through O of n on Pn, minimal toric surfaces, I'll say. This is okay. These are all shellable. And 4 is not really an example, but maybe A tensor, it's closed under products. Okay. Questions? I'm going to need that fact. Okay, so I got 10 minutes left here. So let's return to this example. Again, let's consider O of 1, O of 2 on P2. And the quiver was this one I drew earlier. So I want to write this is O of 1, oh sorry, O of 1, O of 2 are the vertices, and these arrows are the linear monomials, like x, y, and z are the linear functions on P2. And the ideal was xy minus yx was just given by the commutativity relations between these functions. Okay. Then A is KQ mod I is the endomorphism algebra of O plus O of 1, so 2. Okay, and XA was this thing. Maybe I'll label these X, Y, Z, Y, X, Z, right? And it's sitting inside this torus. And then it also had these lines going up through here. Okay. And XA bar is actually a simplicial collapse of this that just looks the same, but you got rid of the orange lines. Right, that picture is not very good. So I'm collapsing, say this guy. So let's try the one here. I could collapse this guy down, but he kind of looks the same. He just stretches out to fit the space. Okay. So I'm just collapsing 3 triangles to get XA bar. Okay. So I'll skip the description of the generators. I'll get to it later. So I want to talk about homological mirror symmetry for P2 in a big diagram. So here's the derived category of P2. And it's an old theorem of Bailenson. that this is the derived category of this set of line, this quiver. There was work in the 90s by Bondal that this was sheaves in the torus with some stratification, which I'll call bundle stratification. Our result is that this is sheaves on. Let me denote the torus by T. It's going to get too small. So T torus. Sheaves on the torus, bundle stratification, sheaves on the torus with stratification. And then these Fan, Liu, Troin, and Zaslow, FLTZ, say that this is sheaves on the torus with their skeleton. That's their stratification. And really derived. These papers don't use derived, don't use this D of, but it is derived. Okay. And then all of these things. So first you can go across these things. I'll do this on the next slide. This is a deformation retraction. And this one is just a deformation. What's called a non-characteristic deformation. And then all of these things are equivalent to, this is by work of Nadler, Zaslow, and Ganatra, Part, and Shiel. The Fukaya category of the cotangent bundle to the torus. Unfortunate notation, cotangent, this is cotangent bundle, this is torus. With this thing, this Lagrangian stop, you could put any of these here, okay? FLTZ is the classic one that's been considered. And then there's further work by GPS that says this is the Fukaya category. So this is the cotangent bundle of a torus. You can think about it as a C star squared. And it has this superpotential X plus Y, so X, Y. And so this final thing you get is called homological mirrors. So this is called the Horivatha mirror. And this thing you get here is equivalence between the derived category of P2 and this category of Lagrangian thimbles for this Lefschetz vibration is called homological mirror symmetry. And in this context, it was done by Uru, Katzerkopf. I guess I'm just using letters. Uru, Katzerkopf, Orlov, and Abu Zaid separately. Okay. Questions? Okay, so I have just a couple minutes. So I wanted to say that this picture is general. You start here with a phonotoric variety, and this arrow was done by Abu Zaid for phonotoric varieties. And then also by FLTZ, they went this way to here. And then this was done later by these guys, okay? So this works for any phonotoric variety at least. And this picture was done for non-phono varieties. this functor is fully faithful for non-Poynting varieties. Okay. I'm going to skip the different stratifications. So I want to say that this is a toric picture here, but this also seems to work. I just have a couple minutes. Maybe I say something really quickly. Also works for green cluster mirrors. This is not toric. Because I'm out of time, I won't explain that. I will just leave it and people can ask me questions, but maybe I should stop there.
Okay, thanks, David. Let's all. Are there any questions? I don't see any in chat. Okay, in that case, David, how does it work for green cluster mirrors?
Right, I threw you a softball there. So there we have W is some kind of Fermat type, or I don't know, Bies-Korn polynomial. And the mirror is the same polynomial. But the difference is that, so I'm going to think of this as the A side. This is the A side. And the B side has this, is actually, this function is on AN mod a group. So I mean the LG green cluster mirror. Okay, and this group is Z, groups of unity acting on this as symmetries of this polynomial. So this is green plus, these are green cluster mirror. These two spaces with functions. These two things are green cluster mirror. And there, so we can take matrix factorizations. Of AN IG with W. This is my B side. This is well known that this is as a representation as K AE1. So this is a shellable poset here. And then this is equivalent to by my result with Jesse Huang, derived category of sheaves. And in fact, this XA bar in this case is basically Rn with this stratification we get. Okay. And then again, if you use, okay, so that this, we got this equivalence. And this thing here is also by this Ganatra-Pardon-Shield result, Fukaya category of CN with a morsified W. So I'll leave it at that. So that says that this B side of the green cluster mirror is the A side, Fukaya category.
Great. Are there any other questions? Okay, if not, let's thank David again.
Hey, thank you.
Okay. See you guys some